So in CD1 of our advanced electricity and magnetism course, we studied about Maxwell equation and we derived how Maxwell equation contains the information for the electromagnetic wave. Now, in this lecture, we'll explore more on electromagnetic wave. So let me remind you what we did last time. So these are the four Maxwell equations that you see here, and the four Maxwell equation gave us the information of an electric field that exists in the form of a wave. So that was the landmark in the history of physics. Maxwell was able to mathematically find an electric field that behaved as a wave. Agreed? Now this equation that you see here is a 3D equation. It's a 3D wave equation. So this 3D wave equation has a Laplacian here, which can be written as del square E by del x square plus del square E by del y square plus del square E by del z square. And this side you have the time part, the time varying part of the electric field. Agreed? So del square E by del t square. Now just a small trick. Now always the velocity is with the time part, because the dimension here, if you look at the dimension here, the dimension on this side is of length square. So the denominator has the dimension of length square. Similarly here the dimension will be length square only if time and velocity multiplies. So when time and velocity multiplies, we get dimension of length, and since we have square terms, so it's a square. So this is a small trick to remember that the velocity of the wave is always with the time part. Now before continuing to explore this 3D Maxwell equation, let us gain some idea behind our 1D wave equation. So before reading this 3D wave equation, we'll try to study the 1D wave equation that we have done in our plus 2. But here a little bit different will do. Agreed? So let me write our 1D wave equation. So our 1D wave equation looks like, so this is our wave equation in 1D. Agreed? So just a little bit of juggling that I've done, and this is nothing but the time varying part, so del square f by del t square, and this is the space varying part. So what is f? So f is a wave function, or I can say f is a wave equation. Now what will be the f dependent on? See, here we have the derivative of f with respect to x, and here we have derivative of f with respect to time. So obviously f is a function of space, that is your x, and time. Remember that we are dealing with 1D wave equation. We are dealing with 1D wave equation. Now question is, how is f dependent on time and space? That we have no idea. So what will be the form of f? We don't know. So let us try to explore this equation. So don't you see this equation is like a square minus b square? Doesn't it look like that? So you remember what we can do with a square minus b square? We can do a plus b into a minus b. So the same thing that I'll do with this. So I'll get, yep, so I can write it in this form. Now let me define two independent variables. So let me define some epsilon. Let this epsilon be t minus x by c. Okay, I'm just defining. This is just a definition. Okay, t minus x by c, and you'll see why I'm defining this. Okay, and I can write eta, which can be defined as t plus x by c. So the power of this definition will come at the end when we write the entire wave equation in the form of eta and epsilon and eta. Agreed? Now question is, what is del by del e? So let us see what happens if I do f. So what is f? F is a function of x and t. So what happens when I do the derivative of f with respect to epsilon? Okay, so that I want to see. So what do I get? Now since f can be either derivative of time or derivative of x. So in the first function, what I need to do is I'll write f, okay, with respect to x, and then I can write this x with respect to, so I can write derivative of x with respect to eta. So why I can do this? There is a reason. The reason is, here you see that x can be written as in the form of eta and e. So x can be written in the form of epsilon and e. Let us see. So combining these two equation, if you add the two equation, what you will get? If you add the two equation, you will get t equals to half. Okay, so t, so when you add these both equation, you get the t, that is a time variable, in the form of eta and epsilon. And when you subtract this equation, you get the x in the form of eta and epsilon. So you'll get x is equals to c by 2 divided by eta minus epsilon. So you can see that my x and t, they are the function of eta and epsilon. Hence here I have written dx by d epsilon. So here I have multiplied a dx here and a dx here. The reason is I cannot write df by d epsilon because f is not a function of epsilon. So I took the help of x. So now what to do? So let me put this in a different position. Now continuing with this our df. So what will be the next term? You see, f is also a function of time, not only x, but f is also a function of time. So you need to write the second part, and that will be now. Now to simplify this expression further, I need to find what is del x by del epsilon and del t by del epsilon. So let me use this. Okay. So what happens when I do del t by del epsilon? Okay, so when I do del t by del epsilon, then you will get a value of half. Agreed? So what you need to do, you need to just do d by d epsilon, and remember that since this eta and epsilon, these are independent variable, so any derivative which will be of form dn by d epsilon is going to be 0 because they are independent of each other. So similarly, what will happen if I do del x by del epsilon? So if I do del x by del epsilon, if you take a close look, then you will get the answer as minus c by 2. Agreed? So you need to put this here, and what do we get? This is what I get. So if I remove the f term both side, then I can see that del by del epsilon can be written as this. So why I have done this? So that if you can go back to your equation, and you will find that here you have got a term like d by dt minus c d by dx. So this term will become what? Del by del epsilon. Similarly, this term, if you do the same calculation, will become del by del eta. Agreed? So now what I need to do is, let me write this equation in the form of epsilon and eta. So I made some now. So we can write this equation now as d. So first term is del by del epsilon. Okay, and what is the second term? Second term is del by del eta into f equals to 0. So what becomes of this? So this will become del square divided by, you see there is a del epsilon part and there is a del eta part. Agreed? So del eta part, and then we have the function. Now this function f is a function of what? Now this function f can be written as a function of epsilon and eta. So now the wave equation takes this form when I write in terms of variables epsilon and eta. So all I have done is I have just made a change in variable. This change in variable was so crucial that it gave us a hint that the f that I am taking will be a function of eta. So that is, it will be a function of t minus x by 2, so x by c, I guess. Yeah, so x by c, or this can be a function of, so this can be either a function of t minus x by c, or f can also be a function of t plus x by c. So this is what we understand when we make a change of variable. So this gives us an understanding that the function f is a function of t minus the space part. So this gives a more better understanding of what the wave function will look like. Now, why this is important? Because now you can guess the solution of a wave equation. So given this, can you guess a solution of wave equation? Yes, one guess will be using, so anything that is a function of t minus x by c. So why don't I use sine of t minus x by c? So this is a solution of the wave equation, but a little bit of dimensional matching I have to do, because you see this has the dimension of time and this has the dimension of time. So I have to multiply something so that this entire thing will be a dimensionless quantity, because sine of whatever sine contains inside is in radians, it is dimensionless. So what do I need to multiply? So cleverly you can understand that you have to multiply an omega, because omega is inverse of time. So yes, so this is what, this is the solution of wave equation, that is sine omega t minus kx. Okay, so where do I get my k? That k comes from the omega and the c part. So you can easily tell that omega divided by c is equals to k. Yeah, this is a very simple expression that you already know. So if you have this omega and you k, then you can find the velocity of a wave. So this is the importance of this thing. So let me just give a quick review of what we have done. We started with 1D wave equation, as you can see from the top. We started with 1D wave equation and we did a change of variable. So these are the change in variable that I did. So 1 and 2. So these are the changes in variable that I have done. And then I wrote the entire function in the form of new variables epsilon and eta. When I did this, I found that my function is a function of, so my wave is a function of t minus x by c, or it can be a function of t plus x by c. So from here I got a clear hint that the wave equation will have this kind of form. Not only I can use sine function, but I can also use cos function. So these type of function, they actually satisfy the wave equation. So that we got the idea of what kind of solution a wave equation takes. Now we can use the same idea and put it into the wave equation found by Maxwell. Agreed? So keep that in mind, what we have taught just now, and let me rub the board. So I need to simplify this big equation. Okay, so how to simplify? Well, you remembered what we did in the 1D case. In the 1D case, if you have an equation that says del square f by del x square, okay, minus, you had what, 1 by c square del square f by del t square. Then you got the solution of this equation in the form of sine, or you can even use cos. So let me use cos. So you can get cos. So what was the form? You got omega t minus kx. You see that this x here is this x here. It is a clear indication that the x that you need to put inside the bracket of the trigonometric function must be the direction in which the wave is traveling. It must be the direction in which the wave is traveling. So what I'll do cleverly here is I will make my electromagnetic wave travel in the z direction. So that will simplify not only my equation but also the solution. So this is what I've done with my equation. Now please see that the electromagnetic wave that I have chosen here as a solution is traveling in the z direction. So if it is traveling in the z direction, can you tell me how the equation is going to look? The equation is going to look as, so this is how it looks. But we are not done yet. Why we are not done yet is, you see the E vector here and you see the E vector here. This E vector can take three components. So this, since this is a E vector, this E vector can have three components: Ex, Ey and Ez. However, very cleverly what I did is I took only the electric field. I assume my electric field is vibrating along the x direction. So let me draw the diagram of how my electric field looks. So consider this is a axis and this is an axis, then, and say this is the third axis. Okay, so then I said that my electric field is traveling along z axis. So this is z, and the vibration, so what is this? This is nothing but this indicates in which direction the displacement is occurring. So the vibration is taken along the x axis. So this is x axis. So my electromagnetic wave, it looks like this. Okay, and here let me draw arrows indicating the increase of electric field with z, and then there is a zero electric field here, and then the electric field oscillates in the reverse direction. Okay, so this is my electric field, and my electric field, it is actually oscillating in the x direction. That's why the amplitude I have written what? It is oscillating in the x direction. So very cleverly I chose my electric field to be in the x direction, oscillating in the x direction. So this equation will further simplify. Okay, so this equation will further simplify. Why I said this equation will further simplify? Because when you do del square by del z square, you have to do del by del z square of all these three terms, but I already assume there is no vibration of electric field in this direction and there is no vibration of electric field along this direction. So I am left with only the Ex term. So my wave equation now simplifies to, so I should write Ex here and Ex here. Note that I have written Ex here after a calculation, and that calculation was doing del square by del z square of E, and when this del square by del z square will act on E, it will act on this y x component, y component and z component simultaneously, and finally only the x component will remain, because I assume my electric field is oscillating in the direction of x component. Now, so you have this equation and you have this solution. Now what else we can do with the equation and the solution? So we can do some more things. So can we apply Maxwell equation to this solution? Let us see what happens. So if I do cross of E, so let me do del cross E. So remember, when we write del cross E, we mean the E that has three components. So what was our E? Our E had three components. Now, as I said, since my electric field is only vibrating along the x direction, so these two things are 0. So can I evaluate del cross E? So let me evaluate del cross E. You remember how it is evaluated? You need to take determinant. It will be I, there will be a J, and there will be a K. With the del part, there will be a del by del x, and similarly we have this. Now I need to write the E components. Now remember that yes, the electric field is vibrating along the x-axis, so it has a component along the x-axis, that is E naught x. Does it have a component along y-axis? No, the electric field is not vibrating along y-axis, and no, the electric field is not vibrating along the z-axis. So when you evaluate this determinant, what do you get? You get, so I get this after evaluating the determinant. Now do you remember by Maxwell equation what was del cross E? Here you can see the first Maxwell equation. So del cross E is minus del B by del T. So what is our aim? My aim here is to calculate B when E is given. So that's my aim. That's why I'm using the equation. So what will happen when I do del cross E? So del cross E is what did I get? I get it is del square. Now E naught Z is the amplitude in the maximum amplitude of the electric field along the x-axis divided by del Z. And this particular term is in the J direction. And this side I'll be having minus del B by del T. This is another important thing, and this is very important because from here we find that the direction of this B vector is in the direction of the J, that is in the y axis. So this is an amazing thing because you see in the diagram when I drew the electromagnetic wave. So what I did, I found that I took my solution traveling along z axis and I took my amplitude of electric field vibrating along the x axis. So what was my electromagnetic wave? This was my electromagnetic wave. So this was the x axis, this is the y axis. And interestingly, from this particular formula we can see that the magnetic field is vibrating along the j axis or along the y axis. So this is a very interesting thing. So from here we can not only we found from Maxwell equation that there are some kind of electric wave and magnetic wave, but we also found that these electric and magnetic wave are actually perpendicular to each other. They are actually perpendicular to each other, and this perpendicularity of electric field and magnetic field is shown by this particular formula here. This formula states directly. We can also evaluate this formula to get more explicit answer. Let us do that. Okay, so can you tell me what will be my B? So this is a differentiation in time, so this will become an integration on the other side. Now, so what is my minus B? So minus B will be just an time integration of whatever is there inside the integrand, that is del square. Agreed? Now can you calculate this part? Okay, so what is this part? So all you have to do is differentiate. Oh, I made a mistake somewhere. Let us see. Here I should have a square. So here I should have a square, and here I should have a square. And one more thing I need to drop. Here I will have only Ex, so here I'll have only Ex, so no E naught. Okay, so no E naught. Now, so now can you tell me what is Ex? Agreed. So when you do double differentiation of this part with respect to z square, what do we get? Oops, made some mistake again. So this will be not square, these are not square. As we evaluated, this will be just dEx by dz. So this is not square, so I was correct. So this is not square. Agreed. Okay, so you can easily see what the mistake done. You can easily calculate this determinant, and you'll find that you'll get del Ex by del z. And here you should take Ex because E contains three parts: Ex, Ey, and Ez. So there should be an Ex. Now what will be the value of dEx by dz? So you can easily evaluate, and you'll find that the value can be written here. So I'm writing it here. Okay, so I'll get, so this is what I get. Now you can easily calculate the integration part here, and you will find that your B vector will come out to be this. So where do I get my C? Remember the formula, omega by C is equals to K. So I have used this formula here. Okay, this is a famous relation. Even you can find this in your wave mechanics, because when you do omega by k, you always get the velocity of the wave, and here the velocity of the wave is c, that we have already calculated in our previous lectures in CD1. So look at this interesting thing. This interesting thing says that the maximum amplitude, that is b naught y. Why I said b naught y? Because this part is in the j direction, I mean the y direction. So it is c times lower than the value of electric field. So the maximum magnetic field, so if I say the maximum magnetic field as b naught, and should I write b naught x? No, I should write b naught y, because the b is vibrating along the y axis. So the maximum value of b naught y is equals to 1 by c of the maximum value of e naught x, because the e naught is vibrating along the x axis. Agreed? So this is a clear indication that the electromagnetic wave has both electric and magnetic field, and these electric and magnetic field are perpendicular to each other, and the value of the amplitude of the magnetic field, the maximum amplitude of magnetic field, is 1 by c times the maximum amplitude of electric field. So this ends your electromagnetic wave lecture here. So what are the 3 points we learn? Point number 1 is Maxwell equation contains, so these are the 4 Maxwell equation. Maxwell equation contains the wave equations. Okay, and that wave equation, when it was evaluated by using a solution, so we assumed a solution of the electric field as this, and when we assume that the electric field is vibrating along the x-axis, automatically the Maxwell equation said that the magnetic field will vibrate along the y-axis. So the magnetic field will vibrate along the y-axis. So this is a clear indication that electromagnetic wave have electric field and magnetic field vibrating perpendicular to each other, and both are traveling in the z direction. Now look at an interesting thing. Oh, there will be a cos. There will be a cos. So I made there will be a cos here. Agreed. So you can do the steps here. So you see a very interesting thing, that there is no phase lag. If the electric field was in cos, even the magnetic field is in cos. So there is no phase lag. So if the electric field starts with from 0, then the magnetic field will also start with 0. And since the here we have taken cos. Okay, so this is the diagram of electric and magnetic field when you take E is equals to E naught sine omega t minus kx. So this is the sine form. Now the diagram for the cos form will look like this. What you have to do is, all you have to do is shift the axis by 90 degree. So here and here. So if you shift the axis by 90 degree, then you are left with an electromagnetic wave that takes the cos term. Agreed? So cos and sine are related by just a 90 degree phase difference. So this is what you understand from electromagnetic wave from the Maxwell equation point of view. Now in the next lecture we'll explore more. Okay,